Hi guys, y'all doing okay today? We have a test on Friday, as you know. It'll be in the auditorium. Come, there'll be a seating chart. Try to get there a few minutes early just so you're seated by 10:40 or excuse me, 9:40. Have a help session tomorrow at 3 p.m. If you're not able to come, you have class or whatever you have, just send me an email. You do get extra credit for attending, but if you can't come for whatever reason, let me know. Send me an email and I'll explain to you how you can still get extra credit for that. Okay? But you can email, I'll send you the instructions. Test is 27, I think, or 28 questions long. It covers all of chapter 1, that's forces and fields, and then part of chapter 2, which includes potential and potential energy. I recommend that you study the old test. They give you a good indicator of what this test will be like. You'll also see questions from the OpenStack, the homework assignments that you had, not the individualized questions, but just the ones that I assigned to you. You'll see some of those. I think I put maybe 4 or 5 questions from OpenStack. They won't be identical or verbatim, but they'll be very, very similar. You'll probably recognize them from OpenStack. All right? Today I'm going to answer questions, but again, we'll talk about the nature of charge on the test, static charges, conductors, insulators, the properties of charge, it's quantized, it's conserved. We've had various questions in OpenStack and in class regarding those things. We'll also see Coulomb's law. You'll have to calculate the force between 2 or maybe 3 charges that are in 1 or 2 dimensions. You'll also have problems where you are just asked qualitatively, if this happens, what happens to the force between these charges? You might have, like we've done in class, where you have a configuration of charges and I ask you to just sketch out or show me which vector is the correct vector. We've done problems like that. You will have a question like that. You'll have also electric fields. That is where you have calculating the electric field due to 2 or 3 charged particles, and then calculating the force that's due to that electric field. Then you might have a simple kinematics problem, like what we've worked in class, but it'll be fairly straightforward, where you calculate the acceleration and then the velocity or the displacement from that. But just remember your kinematics equations. Really, it's just E equals AC and X is 1/2 AC squared. That's not on your equation sheet. Then potential, you have to calculate the potential due to 2 or 3 charges, and then also potential energy. There will also be questions about the work or the energy gained by particles, by charged particles, when they go through an electric field or when they go through a potential difference. There are some problems that we've worked either in OpenStack or in class about those things. All right? What are your questions today? Yeah. You can ask me to give you a problem.
Can you do one that we have to find the velocity of the particle?
Sure. You want me to pull one from the test? Is that what you prefer? All right. Let's see. What do y'all have? What test do you have in your workbook? What year is it? 16. What is this? This is 18, right? Okay, like number 16. This is the spring 15 exam. And number 16 on the spring 15, exam 1. You'll only be looking at exams 1 for this as you're going through the old test. And in some cases, exam 1 will have a few questions about capacitors, so just disregard those. But in this one, I have a 4 Coulomb charge. There's its mass. Oh gosh, that's a big charge. And it's at rest, and then it's released in an electric field of magnitude 50 newtons per coulomb. How fast does it move after 2 seconds? So you have several steps. You have 3 steps. First is you need to find out what is the force. And the force here is going to be Q times E. Q is going to be 4 coulombs times 50 newtons per coulomb. So that's going to be 200 newtons. So this charge has 200 newtons acting upon it. And then I want to find the acceleration from Newton's second law. That's A is equal to F over M, right? F equals MA. So that's 200 newtons divided by the mass, which is 5 kilograms. And then that's going to be equal to 40 meters per second squared. And then I want to find the speed. Well, V is equal to V naught plus AT. V naught here is 0. It'll always be 0 as far as we're concerned for these problems. So that's going to be 40 meters per second squared times the time, which is 2 seconds. So it's 80 meters per second. This could change slightly. Like instead of doing it this way, I could give you 2 charges, and then you would have to calculate the force in a different way. Instead of knowing the electric field, you'd have to use Coulomb's law. But really, it's going to be like this, except this part might change, or you have to use K QQ over R squared. That's the Coulomb's law in order to find the force between 2 charges. Okay?
So, like, the one on OpenStax where it was like circles and line speed. Like,
Yes. Okay, so that's different. You want to look at one of those? Is that what you're talking about? Let's look at the one that was from OpenStax. That was a good question, I thought. Let me just open up a new. So in that problem, and it's due tonight, by the way, so if this helps you, that's great. In that problem, we had some equal potential lines that looked like this. And I forget what it was. I think it was something like one line was minus 100 volts, and another line was, I don't know, let's just say 300 volts. And let's see, was it an electron or a proton? I think it was a proton. Protons move from high to low potential. So if I have a proton right here, it's going to roll downhill, so to speak. It moves from high to low potential. And so it moves from 300 volts to 100 volts. And what it asks is, what is its velocity when it goes through that potential difference? This is very similar to your OpenStax question. We've had questions like this similarly in class. So here, delta V, that's my potential difference. I'll call this point A, I'll call this point B, is equal to VB minus VA. That is potential difference. The difference in potential between 2 different points. And so that's going to be minus 100 minus 300, so it's minus 400 volts. I'm not really going to worry about the negative sign here. I'm just really looking for the magnitude of the speed. So I'm going to leave off that negative sign. But it goes through a potential difference of 400 volts. Now, I know that my energy, or rather, let's start by this, that voltage or potential is energy per charge. And so if I want to know the energy that this object gains, it's going to be equal to Q times delta V. Now if I have a proton, oh, and by the way, this particle is gaining kinetic energy because it's like it's a ball rolling downhill. And so it speeds up as it moves from 300 to minus 100 volts. And so this is going to be equal to 1/2 mv squared. Now in this problem, we wanted to solve for V. For little v, I'll do a script there. So it's going to be 2q delta v over m, square root of that. And then that'll give us what the speed is. Now remember, this is a proton, so I know the charge. It's 1.6 times 10 to the minus 19, and I know the mass. It's 1.67 times 10 to the minus 27.
I think when I solved that one, I did delta V is equal to the change in potential energy over.
That's fine, although we need to recognize that it's losing potential energy, and so it's going to be gaining kinetic energy.
Because aren't they, like, I just like, potential is equal to kinetic, discarding energy is equal to
Yeah, you can sort of think that, but you're really talking about kinetic energy here, because this object is gaining speed, it's gaining kinetic energy. Karen, I think this is really what you were asking the first time, right?
Oh.
They're both good problems, right? And you can see both on the test on Friday. Okay? It's from the OpenStax. But we've done this as well. Know, too, that when you have positive or negative particles, remember how they move. Do they move from high to low potential or from low to high potential? I always forget. So whenever I think about that, I like to draw this figure where I have a positive and a negative plate. And in my mind, I know that the positive is high and the negative is low. And then I ask myself, well, if I had a proton in between those two plates, which direction would it move? Well, a positive charge would move in this direction, towards the negative charges. And a negative charge would move in that direction, towards the positive charges. So positive charges move from high to low, negative charges move from low to high potential. All right, so if I had an electron right here, for example, it would move uphill. A proton would move downhill, so to speak. Electrons act differently than protons. Those are good questions, and you'll certainly see some like that on the test coming up on Friday. What else? When we're talking about fields, forces, potential, and potential energy, it will help you to remember that fields and forces, those are vector quantities. And so when you're dealing with fields and forces, you deal with them like vectors. Potential and potential energy, on the other hand, those are scalar quantities. So when you deal with potential and potential energy, you deal with them differently than you do with the fields and forces. So just sort of keeping that in your mind straight will help you mathematically in how you deal with those things. Things like when I'm dealing with fields and forces, I don't include the negative signs, because those negative signs are already wrapped up in how I draw my vectors. Whereas when I'm dealing with potential and potential energy, I do include the negative signs, because the negative has a different meaning. It has to do with the work that's being done. Remember, if F and D are in opposite directions, it's negative. If they're in the same direction, it's positive. It also helps you in how you add up those things. Like when you're adding potentials and potential energy, you just add them up like numbers. And when you're adding fields and forces, you have to add them like vectors, using your angles and your Pythagorean theorem and your tans and your sines and your cosines. What else?
Are you having like 2D problems?
Yeah, you're going to have 2D problems. Let's look at the old test and work one, okay? In fact, what I've given you is a figure with 2 or 3 charges on it, and I just use that figure for a whole string of problems, like 4 or 5 problems, where I ask you, what is the force? What is the field? What is the potential? Your answers aren't dependent upon one another, so if you get one wrong, that's not going to throw them all off. But you're just dealing with the same figure. That way, make sure you get your angles all right on that figure. It's a common triangle that you'll see. It's either an equilateral triangle or a 3, 4, 5 triangle or something along those lines, something that you've seen before. Let's see. Let's just go back to this one. I'm sure there's one on here. Oh, yeah, so here, like this one right here, I want to know the magnitude of the electric field at point A for these 2 charges. So it'll be something like this, and I'll say, what is the electric field here? I'll say, what is the potential here? What is the force, say, on this charge? Because you can't have a force here, right? If there's no other charges here, you can't have a force. But certainly these 2 charges experience forces. So you want to ask yourself the question, can I answer that question? Can I tell the field and the potential at this point? Can I tell what is the force on either one of these charges? And can I determine the potential energy of this configuration of charges? You want to go through all of those for this particular configuration? Because you're going to have all of those problems. I guarantee it. Let's see, let me put it into my notebook here. It's a 5 and a minus 10. These are nanocoulombs. I try to make it so that the numbers work out nicely. You might have some decimal numbers, and you will have some decimal numbers, but I try to make it so that you have a lot of cancellations. So as you're working through these, make sure you watch for those cancellations. All right, so first, let's just ask, what is the electric field? What is E at point A? We'll call this A. What you want to do there is draw your vectors. So first, we'll call this Q1 and Q2. E1 is in this direction, right? Because I imagine a positive charge at point A, and then ask myself, what is the direction of the force that that positive charge will feel? And it's going to be a repulsive force, and so the electric field is downward. And then E2 is going to be to the right. Because I put my positive charge there, and I say, oh, that's an attractive force. Next, I want to calculate E1 and E2. The magnitude of E1 is KQ1 over R squared. That's 9 times 10 to the ninth. 5 times 10 to the minus 9 divided by 4 meters squared. And so that is 45 divided by 16, whatever that is. What is it? Huh? You're amazing. 2.8 newtons per coulomb. And then E2, I do exactly the same. 9 times 10 to the ninth. The charge is 10 times 10 to the minus 9. Notice I left the negative sign off. In fact, on your equation sheet, you'll see little absolute value bars around that Q value, divided by the distance, which is 3 meters squared. That cancels with that cancels with that, and just leave me with 10. And then if I want to know the net electric field, it's going to be a vector that looks like that. E, the magnitude, is the square root of 2.8 squared plus 10 squared was it C? Does anybody know? Or A? What is it? 10.38? Okay, so 10.4. So that is the electric field at that point. Then you also need to find out what is the angle for the electric field. In this case, you got to do a little trigonometry. Let's see. I would say the inverse tan of opposite over adjacent. E1 was 2.8, E2 was equal to 10. The opposite is 2.8 divided by 10, and then whatever that is, that angle. Uh, 16 degrees? So it's 16 degrees below the plus x-axis. So I'll ask you either for the magnitude and or the direction. Those will be probably two separate questions. Or I might just ask you the magnitude or just the direction. All right, so that's the first part. Now if I want to know the potential, that's probably the hardest part, by the way. If I want to know the potential at that point, V is equal to V1 plus V2. So this would be a third problem. These, the electric field, that's two problems, the magnitude and direction. A third problem is what is the potential. Remember, a potential, vector or scalar quantity? It's a scalar quantity. Okay, so you treat it differently. You treat it quite a bit differently. So I say KQ1 over R1 plus KQ2 over R2. This one's different because I'm going to keep the signs because I'm dealing with a scalar quantity. So that's K, or let's go ahead and put the values in. 9 times 10 to the ninth. Q1 was 5 times 10 to the minus 9. Divided by the distance, which was 4 meters. Plus 9 times 10 to the ninth. 10 times 10 to the minus 9. Whoop, don't forget my negative sign there. If you do, you'll probably get an answer that's also an option. So double check when you're done just to make sure that you've gotten all your negatives in the right place. Divided by the distance, which was 3 meters. Notice these aren't squared. It's KQ over R. I can do some cancellations here. That cancels. That cancels. That leaves a 3 up top. And so I get 45 divided by 4. 11 and a half minus 30. So whatever that is, what, 18.75, 18.8, 19. Say negative 19 volts. So that is the potential at that point. Being careful here with your signs, being careful that you're not squaring these when you're not supposed to square them, but particularly about your signs, that's often where students mess up. And then make sure that you report the answer as a negative, because sometimes I'll put both plus and minus 19 as options, but not always. Okay? Oh, yeah. Rick.
So when you have to find the angle, how do you know which one is on the screen?
Okay, that's a good question. Let's go back to that one. So we're looking at this little piece right here. I'm going to redraw it just a little bit. I'm going to take those red vectors and I'll redraw them like this. This one is 2.8 and this one is 10. And then the green vector, which is really what we're looking for, is that vector. See, all I did here is I translated this vector over to here, and then I get this figure. And, you know, if you've been doing vectors for a long time, then you see that, but it might help you to draw your triangle, especially since it's been a while since we've seen this, since last semester. Now, I'm looking for this angle right here. And so the adjacent side is the 10, and the opposite side is the 2.8. Where was that? Yeah, so we have opposite over adjacent. This is opposite, because it's opposite this angle, and then this is adjacent to that angle. So that's a good question. All right? Let's see. So I might also ask you, what is the force on one of those particles? In which case, I would give you the same particles, a 5 and a 10. I'm going to redraw that. It's just getting messy. All right, so far we've had like 3 or 4 problems that you would encounter. Here's our 5. Here's our negative 10. This is 4. This is 3. And I could ask you, what is the force on this particle? For example, the magnitude and the direction. I'm not going to give you a configuration of 3 charges on 2 dimensions, in 2 dimensions, and then ask you what the forces are. We did an example like that in class, but it gets kind of long and complicated as you're dealing with the vectors, and I'm not going to give you that as part of a single problem. However, you could see something like this. If I want to know the force on that particle, what I would do is first sketch in the vector. I know that the force is going to be in that direction because it's going to be an attractive force. If I want to know the magnitude of that force, it's just KQQ over R squared. This is the magnitude of the force. So I'm not going to take the signs of those charges. So it'd be 9 times 10 to the 9th, 5 times 10 to the minus 9, 10 times 10 to the minus 9, divided by the distance, which is 5 meters squared. And then whatever that is, I don't know what that is right off. But that would be the force. And then if you wanted to know the direction of that force, which I could also ask, and I've asked this before, if I want to know the direction of that force, I want to know that angle. In which case I would do the angle is the inverse tan of opposite over adjacent. The opposite side would be what? The 4 or the 3? Right. So 4 over 3. And that's equal to 53 degrees. The final question that you might encounter on this is just what is the potential energy of this configuration of charges? These 2 charges contain a certain amount of potential energy. What is that potential energy? And so to find the potential energy, I would say, oh, by the way, here, I didn't say this outright, but I would have to find this distance, which is 5 meters. This is a 3, 4, 5 triangle. Just a second, Marissa. It's a 3, 4, 5 triangle, so you just sort of know that. But if you don't know that, use your Pythagorean theorem. The square root of 3 squared plus 4 squared is equal to 5. Marissa?
That would be above the negative x-axis.
Right, 53 degrees above the negative x-axis. Or it could be, what would that be, 137 degrees from the positive x-axis. That's a good point, and I like to do that just to make sure that you're aware of how we're measuring those axes, how we're measuring from those axes. You'll know how to do that. You've all done that, and you've all done it correctly at some point. You just have to do it on Friday. You can do that, right? You're not exuding confidence. Like, I'm not getting confidence from you. Am I getting confidence? A little bit worried. Yeah. Hopefully you're a little bit worried too. But not stressed. But just worried to the point that it prompts you into practice and action and all that. Okay. To find the potential energy, I do KQQ over R. This is a scalar quantity, so we have to include those signs. 9 times 10 to the 9th. Q is 5 times 10 to the minus 9. Negative 10 times 10 to the minus 9. Make sure you include that sign. It's a difference in, as I'm holding these two charges, do I have to hold back so that they don't stick to one another, which is what I have to do here? That's a negative potential energy. Or do I have to hold them together so that they don't fly apart? That would be a positive potential energy. That's what the negative means. And then divided by the distance, which is 5 meters. And then whatever that is, well, it's negative 90 times 10 to the minus 9 joules. Okay? Those are all things that you will certainly see on the test. I don't want any secrets about that. You certainly see those very similar, different numbers, of course, but basically those same questions.
So it's a scalar quantity, that's how we have to worry about the signs, right?
Right. So when you have a scalar quantity, that's potential energy and potential. Those are both scalar quantities. That's when you have to be worried about the signs, when you have to include the signs. If you look on your equation sheet, that should give you some clue. I think this is right. That when you have Coulomb's law, it has absolute value bars around it. And similarly for the electric field, KQ over R squared, it has absolute value bars around it. That means you're going to include the signs. But the others do not have absolute value bars. Kevin? Okay, so a nano is 10 to the minus 9. Remember, so you're going to see these metric prefixes. So just, don't try to get past having to go through all the conversion processes. Say 10 microcoulombs or 10 nanocoulombs. Micro is 10 to the minus 6. So that's 10 to the minus 6 coulombs. Nano is 10 to the minus 9 coulombs. In fact, I tend to use nano more than micro because charges are really, really small. And nano is really, really small. It's more representative of the charges that you'll see. I remember nano because it looks a lot like 9. It has 2 ends in it like 9 does. And it's really small, so it's negative 9. Claire?
Are we going to have a question where it's like converting units? Like, yeah, like when you make this now a volt, and there's something that's like, you might see it in volts per meter, but it can also be joules per coulomb or whatever. Are we going to have a question like that?
You could. You need to know your SI units. But, when you encounter those, go back to your equation. Like, for example, if you want to know what are the SI units of voltage or of potential, go back to our basic definition of potential, that is energy over charge. And so then I know that's going to be joules over coulombs. Or if you want to know what are the basic SI units of joules, we know that this is an energy quantity. So we go back to our 1/2 mv squared, kilogram meters per second squared, meter squared per second squared. Right? So you're really just sort of building off of your equations. Keep going. I don't know how to What's that? Listen, I want our big definitions are electric field is an energy is a force per unit charge, and electric potential is an energy per unit charge. So those are more important in my mind, that electric fields are a force per unit charge are Newton per Coulomb, and electric potential are joules per Coulomb. Yeah, good test taking skills too. Sometimes, often I think even, that information is in the test too that can be used in other problems. So as you're going through the test, look for that to see a little hint here. All right. What else? What? Yeah.
Can you go over number 2 on springs?
This is in the back of your book. All the exams are on this website, you folks, so you can find them there. Sorry. Number what? Okay, so you bring a negatively charged rod near to a neutral copper wire. Which of these statements is true? You get an induced charge in this. So what happens is that I have these negative charges here. They're going to force all the negative charges to that end of the wire, and then you'll be left with a net positive charge on that end of the wire. And so in this case, it has two answers. So it looks like B is right. What is there another one right? Oh, but D is not right. Why is D not right? Positive charges don't move. Right. So the positive charges do not move to the left-hand side of the wire. You're left with an excess of positive charges. But it's not because positive charges have moved through the conductor to that left-hand side. It's only because they're just sort of left high and dry without their electrons. So the electrons, they scooted over to the other side. Protons in a conductor do not move. They're tightly bound into their nuclei. So probably students in this test, they said, hey, there's two answers. And then I reminded them that no, there's only one answer. So you have to pick the best answer. What else? Look, I'll just sort of skim through. We've done a lot of these, so let's go to another one, and then y'all holler out. Make sure you know how to do field lines, how to interpret the charges on a field line. Remember, the ratio of the charges is equal to the ratio of the number of field lines. You understand what I'm saying? That if I have 6 field lines on one and 2 field lines on another, the ratio is 6 to 2. That means the ratio of the charges is also going to be a ratio of 6 to 2 or 3 to 1 or some equivalent of that. Do you hear what I'm saying? The ratio of the field lines on either side is equal to the ratio of the charges. Any of these stand out to you that you want to look at in particular? Yeah.
It's not pretty much to work out if it's going to lose the first one.
The very first
I
one.
don't even know what it's asking.
Okay.
Oh, not on this one.
Oh, spring 16. Oh. Oh, okay. Well, let's think. I mean, you don't have to know what a quark is. You need to know what a neutron is. What is the charge on a neutron? It's 0. It has a neutral charge. That means that all the little charges that make up the neutron, they have to add up to equal to 0. So I have the up quark is plus 2/3 of a charge, and the down quark is minus 1/3 of a charge. And so what I need here is a combination of these that will add up equal to 0. And that has to be the up quark and what? And 2 down quarks. 2/3 minus 1/3 minus 1/3 will give me 0. So that's really what that's testing, not what a quark is. That doesn't
I was just,
matter.
I didn't understand.
Okay. What else, folks? Any on that test that stands out to you that you want to look at? Or do y'all just want to go? Huh? What's that? Give you a hard one, like from here, or just make up one. This is a tough one. Where is it? Number 15. I'm not saying that you're going to have one like 15, but it's a good indicator of sort of, do you understand what's going on? This is spring 15. You don't have it in your book. Here I want to know what is the charge Q so that the electric field over here is 0. Y'all know how you go about that? Well, first, is it be negative or positive, that charge? What is it? It has to be negative, right? They're all negative because my electric field, I'll call this Q1 and this Q2. E1 is going to be in this direction. And so E2 has to be in this direction, which means that this has to be negative. But all the options are negative. And in order for the electric fields to cancel out, what must be the relationship between E1 and E2? Their magnitudes. They must be what? E1 is bigger, smaller, or the same as E2 in magnitude. They want to be equal. They're opposite in direction, but they have to be equal in magnitude in order for these to cancel out and go to 0. So E1 has to equal E2. That is, the magnitude of E1 has to equal the magnitude of E2. And so I would say KQ1 over R squared, R1 squared, is equal to KQ2 over R2 squared. We haven't worked a problem like this, but you should be able to work a problem like this. The K's cancel. Now put in my values. I have 2 coulombs divided by R1, which is 2 squared. It has to be equal to Q divided by 4 squared. So what's that? Q is equal to negative 8 coulombs. All right, Marissa?
What number on screen in 2016?
C is the answer. Fur is left neutral. Yeah, so I'm rubbing a piece of fur on a rubber rod, and it gives the rod a negative charge. What happens? Well, let's say I started out with a neutral rod, and then this is the fur or whatever over here. And then when I left off, they were both neutral, right? They both had equal numbers of positive and negative charges. But then in the end, this was left to be negative. And so what happened is that the electrons that were on the fur, they jumped off on to the rod. And
No, it's
uh-huh. Somebody was asking about this. So it's an insulator, right? That's what you're thinking. Is you can't have charges moving around an insulator, but you can deposit charges onto the surface of an insulator. And that's what happened here. These others can't be trite because the fur is not left neutral. In fact, the fur is going to be left what? Positive or negative? Positive, because I've removed electrons from it. From what it was before, neutral, and then I removed electrons. The fur is not charged negatively, it's charged positively. And protons are not removed from the rod. That's just verboten. That's not something that we do because it's too difficult to remove a proton. Good question. Yeah. Number what? Sure. Oh, yeah. So this one looked complicated. But if you think about it a little bit before you jump into working it, it becomes a lot simpler. Because I want to know the force on this 2 nanocoulomb charge, and I got 3 other charges. And so it seems like, gosh, it's going to be very difficult. I'm going to have to deal with all sorts of vectors and adding them up and all that. But notice that I have 2 charges that are equidistant and the same. So both of these are going to exert equal but opposite forces. So I don't even need to consider those. All right, let me just draw the vectors, and then I'll get rid of them. Because I'll have a vector that's in this direction for the one on the left, and a vector that's in that direction for the one on the right. But they cancel out, so I'm not even going to worry about them. I'm just going to get rid of them. You follow what I'm saying there? So really all you got to worry about is the 5 nanocoulomb charge. And so that force is going to be K times 2 times 10 to the minus 9 times 5 times 10 to the minus 9 divided by 3 squared. I think the answer is C there. Yeah, C is the answer. Yeah.
Even if you did, like, just say that they weren't the same, and you couldn't cancel it.
Uh-huh.
You would just add up each individual force range to the
You're right, yeah. It's actually not that complicated. Let's imagine that. And I'm not going to give it numbers, but we'll just step through. And what if those 2 vectors didn't cancel out? Say... Let's say instead of this being minus 10, let's say it was minus 5. And so I had a vector that's that big in that direction, and that big in that direction, and that big in that direction. What you would do is first you would calculate the magnitudes of all the forces, and then you would subtract these 2 magnitudes, right? And then you would take the two resultant vectors. If you have one in this direction, that would be a little bit smaller than this one because I've subtracted this. And then the one in the y direction would still be the same. And then to find the magnitude, you do the square root of the squares, the sum of the squares, which we've done. So yeah, it's not an absurd question for the test. You could see one like that, but with different charges on either side. That one? Does that help? Yeah. What else, people? Totally well on the first step. Okay. Yeah.
So can they be neutral static electricity because it just versus the force, or is it because of the magnetic?
Can you repeat that?
So static electricity is neutralized by the magnetic because of the
Oh,
forces, or because it like spreads out?
because water is a polar molecule, and it's slightly more negative on one side. It's like the water molecules take away the excess charge. They just take away excess charge really easily. Because it's polar. That's the important phrase there. That is polarized, or it's polar molecule. Okay? We'll have another help session tomorrow at 3. I understand a lot of you are in the lab, and I'm sorry for that. But if you can't come, you can send me questions. You can always come see me. Students come see me like all the time. And y'all are certainly welcome to my office to come see me. If you have questions, I'm not going to yell at you. I'm not going to hit you. I'm not going to be mean to you. I'll just answer your questions and then send you on your way. Okay? All right, y'all have a good day, okay? I'll see you either tomorrow or I'll see you on Friday, but not in this room. We'll be in Pelcha Auditorium.